So today we'll be starting with the limit state method for columns, and this will be using IS456 2000 again. And starting with this, we'll be first going with the short columns. We'll be designing short columns, certain numericals, and after that we'll be designing columns with bending. So first it would be just columns with actual load, simply actually compressed column, and the second one would be the buckling analysis of column as well. Okay, so to start with that, let us first learn some terminologies. So first terminology is unsupported length. So what is unsupported length in a column? There is a huge description of unsupported length that is given in clause 25.1.3. Now I won't be going reading the entire clause. Let me explain it to you in this diagram. So this diagram I have taken from Design of Reinforced Concrete by N. Subramaniam. So here he has shown in a very nice way what exactly unsupported length is. So basically this first image that you are seeing, that is an image of a flat slab. Now flat slab, this term must be new for undergraduate students. Flat slab is nothing but the system where you completely eliminate the beams. So there is only slab and there is column. There are no beams. The slab itself is well reinforced and it is able to support the load. So this is a new modern kind of technology, and a lot of places this flat slab construction is used. In such a case, the unsupported length will be here you can see from the top of this bottom slab. This is the bottom slab, this is the top slab. So top edge of the bottom slab and bottom edge of the top slab, till that whatever length is there, that is column. The second diagram that you can see, this is also a flat slab construction, but here you can see something, there is a protruding edge. This is called as drop in a flat slab. This terminology is called as a drop. And if you want to learn more about flat slab, it is given in IS 456. It's a separate chapter that is given in IS 456. You can always read that. But here now the unsupported length of the column will be from the top of this bottom slab till the bottom of this drop, and not the slab but bottom of the drop. Okay. The third one, again this is a flat slab construction, but here you can see a flat portion is there, that is called as column head. Okay, so the unsupported length will be from the top edge of this bottom slab till the bottommost point of this column head. Okay, or it is also called as column capital, as here it is written. Then the last one, this is our normal construction using beams and columns. So you can see there are beams here. Now here it is very important that unsupported length for a same column, a column can have two unsupported lengths, one in the either direction, in the x and in the y, and also in other directions if the condition is such. So how it has different unsupported lengths? First you can see this is the y direction, this is the x direction. So in the y direction the beam is much deeper as compared to the x direction beam. So the unsupported length is from the top edge of this bottom slab till the soffit of the beam. This is the bottom part of the beam is called as the soffit of the beam, or bottom of anything. Like this would be called as the soffit of the slab, or this again the soffit of the drop, like that. Okay, so this is the soffit of the beam, and similarly here you can see the beam is much smaller in depth. So obviously this length is going to be different from this length. So a same column can have different unsupported lengths in x and y directions. Okay, moving on to the next one, effective length. Now effective length is length between points of zero moment or points of inflection. This is the most simplest definition. Okay, this is not even a definition, this is just an understanding. The exact definition I have not written here. So what it actually means is that, for let's say this is the first case, and see, whenever this why we actually need effective length in columns is because in columns have different end conditions. A lot of columns are subjected to different end conditions. So the end conditions, for example, here the bottom part is fixed and the top part is also fixed. In the numerical, it won't be given that the bottom is fixed and the top is fixed. It would be given that it is effectively held in position and restrained against rotation at both ends. So held in position means it cannot move, and restrained against rotation means that there cannot be any rotation at this point. So that means that it is obviously a fixed support, and when it says at both ends, it means the both ends are fixed. So when both ends are fixed, generally the deflection is like this. There won't be rotation first of all here, okay, and then there is a slight curvature, and then again there won't be rotation at the bottom part. So you can see that if you draw the bending moment diagram for this, then the bending moment diagram would be something like this way. Okay, just a minute, let me draw it properly. It would be, yeah, this is negative, negative and positive. Okay, so the bending moment when it is seen from this way. Okay, now the points of inflection would be, first of all, this point, second is this point. Theoretical value of effective, so what, this is the effective length. Okay, it is a point in between points of zero moment or point of inflection. So this is the effective length actually, and for both ends fixed, theoretical value of effective length is, this is just 0.5 times the total unsupported length. Okay, so it is 0.5 times L. This is the theoretical value, but recommended value by IS 456 is 0.65 L. So this is the value that we will be taking. Theoretical value would be 0.5 L, that is, this is almost half of the total length, total unsupported length, but theoretically we should take it as 0.65 L. Then the next case, effectively held in position at both ends, so both ends cannot move, restrained against rotation at one end. So only one of the end is restrained against rotation. It means only one of the end is fixed. At other end there is a rotation possible, but there is no movement possible. So this end is a hinge, this end is fixed. So it is not given which end is restrained against rotation and all, but from the diagram we can understand that this point is getting rotated. So I will say that this is a hinge, this is fixed, and for such a case the theoretical value is 0.7 but recommended value is 0.8. Next one, effectively held in position at both ends but not restrained against rotation. So both ends can rotate but they cannot move. So this is also a hinge, this is also a hinge, and theoretical value is 1 times the unsupported length. Recommended value is also 1 times the unsupported length. That means total full length. Next case is effectively held in position and restrained against rotation at one end. So this end is fixed. Next, what it is saying is, and at the other restrained against rotation but not held in position. So this point can move now but it cannot rotate. So this is kind of a fixed roller, we can say. Okay, so it is a fixed roller. This type of support would be called as a fixed roller because it does not allow rotation to happen, but it can move in a translational manner. Like how a roller can move in a translational manner, same way this can move, but it does not allow the rotation. So in such a case, the theoretical effective length is 1 times L, but recommended value is 1.2 times L. Next case, effectively held in position and restrained against rotation in one end. So this is a fixed end, and at other end partially restrained against rotation but not held in position. So here it is partially it can rotate, or in modeling condition we call it as a rotational spring. Okay, so there is some stiffness to it, stiffness to the rotation. It is not expected you to know at this stage, but if you go on to model this into a software, it would be a rotational spring kind of thing. Yeah, so fine, this is the bottom part is fixed, the top part is a fixed roller with a rotational spring sort of thing. Okay, so the recommended there is no theoretical value for this because it will depend on how much rotation and all is allowed. The recommended value is 1.5 times L. This is on the conservative side. So if considering all the safety and all, it is there on the conservative side. Effectively held in position at one end but not restrained against rotation, and at other end restrained against rotation but not held in position. So this end is a hinge and the top end is a fixed roller. Why fixed roller? Because it cannot rotate at this end but it can move. So the theoretical value of this is 2 times L. The effective recommended value is again 2 times L. The last one, effectively held in position and restrained against rotation at one end. So this is fixed and but not held in position nor restrained against rotation at other end. This is free. So this last case is nothing but your cantilever. Okay, and for cantilever the theoretical value is 2 times L. The recommended value is also 2 times L. Fine. So these are all the cases that you have to remember. Now next is slenderness limits. Slenderness slenderness limits are given by slenderness ratio, and slenderness ratio is what tells us how slender a column is. So slender means something that is very small in height to its width. That is a very vague definition of slender, to be slender. But here when we talk in engineering, we have to talk with certain values. So we have devised something called as slenderness ratio. L effective upon D is a slenderness ratio, and if that slenderness ratio is less than 3, then it is called as a pedestal, because pedestal is a compression member where the effective length of which does not exceed 3 times the least lateral dimension. So this D is the least lateral dimension. So let me draw a column here. Okay, this is a cross section of the column. This is D, this is B. So the least lateral dimension is the lesser of both of these values. So if that L effective by D is less than 3, it's a pedestal. Second, if L effective by D is less than 12 but greater than 3, then this column would be called as a short column, because here in clause 25.1.2, short and slender compression members, a compression member may be considered as short when both the slenderness ratio LEX by D and LEY by B are less than 12. Now why these two ratios LEX and LEY are given? Simply because first of all, these are effective lengths, and let me write a general formula. L effective is K times L, where this is an unsupported length, and this K we saw for different conditions we have different recommended values. So this is a general formula for effective length, but we are multiplying it by unsupported length, and we saw that unsupported length is not just one, but it is LX and LY. So it can be in two different directions, different unsupported lengths will be getting. So that's why here LEX is L effective in X direction, LEY is L effective in Y direction, and that B and D are the respective depths in those directions. Okay, so this type of column, if it is less than 12, then it's called as a short column. So pedestal is also a short column, but it is too short, like it's like less than 3, so it's too short. Okay, then L effective by D, if it is greater than 12, it would be a slender column from the same clause. And the last one is, if L, that is unsupported length, upon least lateral dimension is greater than 60, then according to clause 25.3, which is the slenderness limits for columns, the unsupported length between end restraints shall not exceed 60 times the least lateral dimension of a column. So this, if a column has a slenderness like this, it is not allowed. You have to revise the depth of the or the length of the column, either of them. Okay, so after slenderness limits we have minimum eccentricity. Now eccentricity is something that comes from the loading, how a column is loaded. So generally a column, to a column a beam is attached, correct? Beam is attached to the column, and there would be multiple loadings that are there on the beams. So this beam is going to transfer everything on the column. Like on the either side it will have two columns, so it will transfer half of the load here, half of the load there, or by whatever analysis it is going to transfer on the column at the end. Along with a load transfer, it is also going to transfer a moment. So in that case the column is already going to have a moment with it. So in that case the eccentricity will be given as M divided by P, that is the moment that is coming due to this beam here, divided by P, that is the axial load that this beam is going to put. Okay, so P into eccentricity is going to give you the moment, or E is equal to M by P. That is the general case. But in case where this nothing is given, only axial load is given, in such a case the IS code says that all columns should be designed for a minimum eccentricity equal to unsupported length of column by 500 plus lateral dimension by 30. So Lx by 500, this is the eccentricity in x direction, this is the minimum eccentricity, plus dx by 30, subject to a minimum of 20 mm. So this eccentricity what we are calculating here, it should be greater than 20 mm. If it is not greater than 20 mm, we have to take this value. Okay, or in y direction, Ey minimum would be Ly by 500 plus dy by 30. Again that should be greater than 20 mm. When biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum of about one axis at a time. So when biaxial bending means we are considering this column to bend like this in this direction, and also like this, like in this direction. So in both the directions it is going to bend. Such case also we will be doing later on. So in this case, in biaxial bending, both the eccentricities we have to consider one by one. Again, these are the minimum eccentricity when nothing is given, but when the moment and everything is given, when the actual eccentricity is given, then we have to take that actual eccentricity and not this minimum eccentricity. Okay, and we have to check whether that actual eccentricity is greater than 20 or is greater than this minimum eccentricity or not. Okay, so if actual eccentricity is greater than minimum eccentricity, that should be considered in design calculation, and vice versa also. I am saying that if minimum eccentricity is greater than actual eccentricity, that should be considered in design calculation. Now load carrying capacity of short column. So first we will be starting with the short column. In the clause 39.3 of IS 456, it is the load carrying capacity is given for short actually loaded members in compression, and it is PU is equal to 0.4 FCK AC plus 0.67 FY ASC, where PU is the axial load, factored axial load that is coming on the column, FCK is the compressive strength of concrete, AC is area of concrete. So let's say this is a column and it has steel like this. So area of column will be the one that is excluding the steel. Okay, this would be the area of area of concrete. The one would be the one which is excluding the steel, and ASC would be the one which is your steel itself. So ASC is the area of longitudinal reinforcement and AC is area of concrete. Now something extra is given here about the minimum eccentricity. We shall understand it by this clause 39.7.1. the additional moments MAX and MAY shall be calculated by this following formula. So this actually does not come under short actually loaded members, but I am proving you by this formula how the next statement of our clause comes. So what it is given is MAX is PD upon 2000 into L effective by D square. So I won't take X and Y, I'll just write a generic formula. I told you that M by P was eccentricity. So eccentricity E is M by P, this P I took down, that will be equal to D by 2000 into L effective by D the whole square. Correct? Now for short actually loaded columns, if you remember, L effective by D had to be less than 12, only then it is a short column, right? So I'll take this as 12, the extreme case. So E is equal to D by 2000 into 12 square. When I solve this, I will get E is equal to 0.072 D. This should be the eccentricity for a short actually loaded column, but IS code, this clause, it says that it should be 0.05 times. So for it to remain a short actually loaded column, the eccentricity should not be exceeded by this value, but to be more safer side, IS code says that it should not be exceeded 0.05 times the lateral dimension. So however, IS 456-2000 limits this value to 0.05 D. So if minimum eccentricity is less than 0.05 D, then it can be designed as a short column. If it is greater than 0.05 D, then it has to be designed as a column with uniaxial bending or biaxial bending. Now reinforcement details. Reinforcement details for columns are given in clause 26.5.3. First is for the longitudinal reinforcement, and the first clause says that minimum steel that should be given in column is 0.8% of the cross sectional area, and the maximum steel should be 6% of the cross sectional area. But there is a note here for the 6%. 6% reinforcement is practically difficult because it is going to congest the area of the concrete a lot. So the concrete won't be able to move effectively through the column. Where bars from the column below have to be lapped with those in the column under consideration, percentage of steel shall usually not exceed 4%. So generally what happens in construction, you might have seen that after a column is cast like this, some bars are left outside so that the next column can be cast over it. Correct? So these are called as lapping bars. These bars would be lapped with the next column that is going to come. So this distance is called as the lapping distance. And in such case, if you are considering 6% already here in this top column, if you are considering the in reinforcement to be 6%, when it is going to be lapped, that reinforcement will again increase. It will become more than 6%. So that would be like a chaos while concreting. Correct? So in such case, this 6% criteria need not be followed. Point C of that same clause of clause 26.5.3, this was till B. Then C is what the minimum number of longitudinal bars provided in column shall be 4 in rectangular. So if it's a rectangular, minimum 4 bars should be provided. If it's a circular, minimum 6 bars should be provided. The bar dia shall not be less than 12 mm. Correct? Then the reinforced concrete column having helical reinforcement shall have at least 6 bars of longitudinal reinforcement within the helical reinforcement. So actually this helical reinforcement is nothing like it's like a spring that you can imagine it to be like spring, okay, and it is generally given in circular columns itself. So for the circular columns we have already finalize that there will be minimum 6. So that's what this point also says. In a helically reinforced column, the longitudinal bars shall be in contact with the helical reinforcement and equidistant around its inner circumference. So these bars are supposed to be at equal distance from each other, and the helical reinforcement will touch all of them. Maximum spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 mm. So like for example, if the dimension of this column is 500 by 600, let's say, so definitely the spacing between these two bars is going to be greater than 300. So it is not that since in rectangular it is said that only 4 bars are minimum, so I'll provide only 4 bars. No, if the distance between them is too high, you will have to provide a bar in between. Same way here. Okay, so those bars need to be provided, and maximum spacing should be less than 300. Minimum steel for pedestal is 0.15% of the cross section area. So that is the last point. Now the transverse reinforcement details. The first clause is for the diameter of the transverse reinforcement detail. The diameter of the polygonal links or lateral ties shall not be less than 1/4 of the diameter of the largest longitudinal bar, and in no case less than, there is a mistake here in IS code, this clause. It says 16 mm, but it's actually 6 mm. Okay, so it should not be less than 6 mm, but IS 13920/2016 recommends that minimum dia has to be 8 mm. So we will stick to this clause, this code, and not IS 456 for minimum dia, because IS 13920 is specifically made for detailing purpose of seismic structures and other structures as well. So ductile detailing we call it. Therefore minimum dia would be 8. Okay, and these are those transverse reinforcement. These yellow ones that you see, and the blue ones are your longitudinal reinforcement. Next is pitch and diameter of lateral ties. So the pitch of transverse reinforcement shall not be more than the least of the following. Pitch is nothing but this distance, the vertical spacing we can say, the least lateral dimension of the compression member. So from following 3 criteria, it should be the minimum of them. So this is least lateral dimension. Next is 16 times the smallest diameter of the longitudinal reinforcement bar to be tied. So 16 times dia of smallest, and third one is 300. So out of these 3, the minimum would be your pitch. Next, detailing of transverse reinforcement. So the first detailing, if the longitudinal bars are not spaced more than 75 mm on either side, transverse reinforcement need only to go around corners and alternate bars for the purpose of providing effective lateral supports. So what it is saying is that in a column, if bars are like this, there are a lot of reinforcement bars, and this is the first lateral tie around all the bars, then actually the lateral tie has to be provided for these inner bars also, theoretically speaking, but according to this clause, it gives us some relaxation for that thing. So if the spacing is less than 75 between these bars, between the longitudinal bars, then what it is saying is that you don't have to provide this transverse reinforcement at all the bars. Okay, you can skip alternate bars and you can provide like this. Okay, so you can skip these alternate bars for that, and you can provide a reinforcement. This is the first detailing if the spacing is less than 75. Then if the longitudinal bar spaced at a distance of not exceeding 48 times the diameter of the tie are effectively tied in 2 directions, additional longitudinal bars in between these bars need to be tied in 1 direction by open open links. So this type of link is called as open link, and we can use them when the distance between the longitudinal bars, extreme longitudinal bars, are less than 48 times the dia of link. This is called as link, or the transverse reinforcement that we are calling. It is also called as a link. So if this distance is less than 48 times dia of link, then in between we can only provide these open bars. Okay, so these are your open links. Open links, and these would be called as closed links. Fine. Third one, when the longitudinal reinforcing bar in a compression member are placed in more than one row, effective lateral support to longitudinal bar in inner rows may be assumed to have been provided if, what this clause is, like if you have longitudinal bars inside. Okay, so these are the inner rows of longitudinal bars. So it is saying that we can assume that these inner rows are having effective transverse reinforcement if transverse reinforcement is provided for the outermost row in accordance with the 26.5.3.2. so if this outermost row is provided with a good, and according to the clause, if it is provided correctly, that is one condition. And second condition is no bar of the inner row is closer to the nearest compression face than 3 times the diameter of the largest bar. So these inner bars, what we are talking about, they should be greater than 3 times the diameter. Only then the transverse reinforcement can be provided only in one direction. Otherwise we would have to provide them like this also. So generally transverse reinforcement for longitudinal bars generally have to be provided in 2 directions, but this clause is exempting us. It is giving that exemption that if the distance is greater than 3 times diameter from the compression face, then we can provide only in one direction. Okay. And the last one, where the longitudinal bars in a compression member are grouped, not in contact. So these are called as the grouped bars. When a column is very large, what we can do is, instead of providing single reinforcement, we can group those reinforcement, and they shouldn't be touching. Okay, no reinforcement should be touching to each other, and every individual group will have its own link, as you can see here, right? So yeah, what it is saying is, and each group adequately tied with transverse reinforcement in accordance with 26.5.3.2. The transverse reinforcement for the compression member as a whole may be provided on the assumption that each group is a single longitudinal bar for purpose of determining the pitch and diameter of the transverse reinforcement in accordance with 26.5.3.2. The diameter of such transverse reinforcement need not exceed 20 mm. So what it is saying is that when you want to determine the properties of this transverse reinforcement, that is the one that will go around all these groups, then at that time individual groups that are shown here, they can be considered as a single reinforcement. Okay, they can be considered as a single reinforcement, and the diameter of this single reinforcement should not exceed 20 mm. Okay, so effectively you can consider a single dia, but it should not exceed 20 mm, and using these diameters then you will determine all the properties of your link. So these will act as your longitudinal bars, single longitudinal bars. Actually it is a group, but this clause asks us to take it as a single dia bar, and then we can calculate further. So that's it for today's lecture. In the next lecture we will be solving some numericals. Till then, take care. Thank you.